Looking back at last week, if you remember, we had we worked on a boiler system. Oh, I hadn't renamed all of these. Let's just do that now. So this one should be
Oh.
You can't have spaces. And that one, hot water valve. Yeah. So what we got is, if you remember, we had heating on, hot water on, room stat, tank stat, and we had our circuit was, this was A, B, C, and D in that order when we were looking at it last week. It's always useful to put more meaningful names against your inputs for the full proper circuit diagram. And we've had I and C, sorry, or with C and D, and then the valves, one come off I and C, and the other one off B and D. And then this output is the boiler output. So if I run that with all the switches off, we don't get any outputs. If I turn the heating on and I turn the room stat on, I get the boiler and the heating valve turn on, and the tank doesn't make any difference. Yeah. If I turn the hot water on, room stat doesn't make any difference. The tank stat turns the boiler and the hot water valve on. And then if I turn on both and turn on both stats, I get all three outputs on. So from what we had first go off, that quite complex circuit, lots of gates on it, we actually reduced that down using those Carnot maps to 3 gates, 2 AND gates and an OR gate. Okay, you are happy with that? Yep.
Yep.
Right, stop that. Stop the share. And I will now move on to this afternoon's session. Share content, screen. Right, so digital systems. So what we're going to have a look at this afternoon is how digital electronics and the digital system can be used in systems in engineering. So what we're going to have a look at is the binary and decimal number system and conversion between them mathematically. How we would represent negative numbers in digital systems. We're going to have a look at another system called binary coded decimal, which is used so that we can display numbers on, for example, a 7-segment display. And then finally the digital representation of analog signals. So how we can take an analog signal and convert it to digital. We won't go into the detailed electronics of how that happens. We'll go into how an analog signal is represented digitally and one of the issues with doing that. Okay. So binary to decimal conversion. So being able to convert binary to decimal, that's base 2 for binary to base 10 numbers and back again, is quite important to help you understand binary systems and logic circuits. Okay, so in the decimal counting system, we use numbers to the base of 10. So to do that, we use digits 0 to 9. So the number 210, there's 200s, 110, and 3 single digits. Yeah. So each integer number has values of units. So we got the tens, the hundreds, the thousands, and so on. So mathematically, that's based on the 10 to the power of index notation. So 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, and so on. Yeah. Then when we want to represent numbers smaller than 1, we go 10 to the power of minus 1, which is a tenth, to the minus 2 is 100th, to the minus 3 is 1,000th, and so on. And they're all pretty much familiar with that system anyway, with our engineering unit multiple systems. Yep. And move on. So the value of any decimal number is equal to the sum of its digits multiplied by the respective weights. So for example, number 6163 to base 10, 6,163. We've got 6 times 1,000, 1 times 100, 6 times 10, and 3 times 1. Yeah. Where in this decimal numbering system example, the leftmost digit is the most significant. So in a numbering system, the digit that gives you the 1,000 would be the most significant digit. Yeah, and then the units is the least significant. Yeah. So a digit 6 is the most significant in that number, and the digit 3 is the least significant. That's the right hand most number. Okay. Move on.
Move on.
Yeah. So when we represent a binary number, in the decimal number system, the weight of each digit from right to left increases by a max factor of 10. In the binary number system, the weight increases by a factor of 2. So as we go up, we've got the units, as I usually like to call them, the 2s, the 4s, the 8s, 16s, the 32s, 64s, 128. So each one is a multiple of 2 as you move up. The least bit significant digit bit being, in this case, 1, and in this 1, 2, 3, 4, 5, 6, 7, 8 bit representation, the most significant bit is worth 128. Yeah. Okay.
Yeah.
But remember, in the binary number system, each of these digits can only either be 1 or 0. They can't be anything else. Yeah. So if we want to convert binary to decimal, we can think of the decimal number in a table like this. We're working from right to left. We've got the 1s, the 2s, the 4s, the 8s, 16s, and so on. So if we got this binary number 1011001001 as shown. We've got 256. We've got a plus 64 because we got one of them. We've got a plus 32. We've got no 8s, no 16s. We've got a plus 4 and we got a plus 1. We add all them up and that equals 357 base 10. Yep. So the numbers working from left to right, most significant, MSB, LSB in any number. Yep. So in summary then, we can convert binary to decimal by finding the decimal equivalent of the binary array of digits. So they go up in a series to base 2. Numbering system, any numbering system uses the subscript to say what the base is. So this 1100012 means base 2. We don't normally put the base for numbers in a decimal system. So if you don't have a base, it's assumed to be decimal. We could have 67 base 8. We could have IF base 16, which is called hexadecimal. We're not going to go into those numbering systems. They're just examples. Okay. But what we're interested in is the decimal system and the binary system. All happy for me to move on?
Yeah.
Yeah. Right. What I'd like you to do then, about 5 minutes, use the table you've been given. So there's the most significant bit is 128. The least significant bit in the table is 1. And so convert those binary numbers into their decimal equivalents. All right.
I could totally go to the grocery store like this because my mouth is covered. If someone looked at me in the eye, I'd be like, "What? It's Corona."
Right then, what do we got? 1011. What does that equal? I'll get an answer sometime this afternoon.
Which one?
First one.
First one is 11.
Yeah, that's 8. You got the 8 plus the 2 plus the 1 equals 11. Maka, what about the second one? Oh, he bloody turned his microphone off.
19.
What? 19, yeah.
I
You're,
was wondering where you get, because on the example you got 357 to the 10. Where do you get that from?
what, in this example?
No, just in the one. Yeah.
Yeah. 256,
Yeah.
64,
Yeah.
32,
Yep.
4, and 1.
Yeah.
Does that not add up to 357?
Yeah,
Yeah,
but
it
why did
does,
you put the
yeah.
10 there?
That's just to say that the number is to the base 10.
Okay.
We wouldn't normally do that on decimal numbers, Macaulay.
Okay.
Yeah. We normally leave it off for decimal and just assume decimal. All right.
All right.
Yeah. So in this one, you've got 16 plus 2 plus 1 is 19. What about C?
Was it 202?
It is 202, Nathan. Yeah. made up of 128 plus 32, sorry, plus 64 plus 8 plus 2. Yep. And the last one,
$119.
yeah, made up of 64, 32, 16, 4, 2, and 1. Yep. Okay, so I was fairly easy task to work out the decimal value of a binary number. Yep. Okay, so those binary numbers we looked at so far, depending on how many digits you have in your binary number, they can represent numbers up to a certain size, positive integers. So from zero, so a 4-bit binary number can represent decimal numbers from 0 to 15 and they're integers. Okay, so in maths, positive numbers including 0 are represented by unsigned numbers. So in normal mathematics decimal number system, we assume a positive sign in front. We don't normally put that. Okay, when dealing with negative numbers, we in normal numbering system, we put a minus sign in front of the number to show that it's negative in value and different from a positive unsigned value. Similar is true for signed binary numbers. The digital system, as we know, can only be represent 1 or 0 for each digit. Okay, so there's no provision in that system to have a plus or a minus sign to represent the sign of the number. So what's done is the most significant bit of a binary word is used to represent the sign of that binary number, positive or negative, and that's shown in detail on the next page. So if we take an 8-bit word, the 7 digits, least significant digits of that word represent the magnitude, the number, in this case 53. The fact that the most significant bit is 0 indicates that there's a positive 53. The same number but negative, we see we've got the same digits to represent the number 53, the magnitude 53, but then the most significant bit is 1, saying representing that it's equal to minus 53. So we have to use we can either look at it as we have to use an extra bit, or that we lose a bit from the word. So there's implications of that for obvious reasons on the size of the number that can be represented by a given number of bits if it's going to be a signed binary number. Okay, so the most significant bit in a binary number, if it's signed, represents whether it's plus or minus, and that's, you set it to 0 for a plus and you set it to 1 for a minus. So what that means is, if we take an 8-bit unsigned word, it can represent between 8 zeros to 8 ones, which is between 0 and 255 in decimal. So it can represent numbers between 0 and 255. If we make that 8-bit word represent a signed number, then it's 111111. That's negative, because this first bit is 1 and this first bit is 0, so that's positive. It goes from minus 127 up to plus 127. So we still have 256 digits, but half of them are positive and half of them are negative. Yep. So if we wanted to represent minus 255 to plus 255, we'd have to add one more bit to the binary word. Okay. So on that note, another 5 minutes or so, use the table provided to convert these signed binary numbers to their decimal equivalents.
Signed binary numbers.
It means that you have to take consideration of whether it's a plus or a minus number. Moving on a bit further then. Converting decimal to binary, so this is going the other way. We want to got a decimal number, and we want to convert it to binary. We can use what's called repeated division by 2 method. So this is a relatively easy method to convert a binary number to its equivalent decimal number by continually dividing a result by 2 and finding out whether you get a remainder or not. Okay. So, for example, if we got the decimal number 294 base 10, we want to make it a binary equivalent. We start off by dividing by 2. And because that's an even number, we get no remainder, so the least significant bit is 0. Can we take this result here, 147, and divide that by 2? We get 73. In fact, if on your calculator you'll get 73.5. You've got a remainder 1. So that's your second digit there. So currently, working from left to right, we got 01. Then we take the 73, and divide that by 2. It gives us 36, remainder 1. So we've got another 1 digit. Divide 36 by 2, we get 18, remainder 0. Then we divide 18 by 2 to get 9, again, remainder is 0. We divide 9 by 2, we get 4, remainder 1. We divide 4 by 2, no remainder. We divide 2 by 2, we get 1 with no remainder. We divide 1 by 2, we get a remainder 1. No significant bit. So that by that method of continually dividing by 2, and all you're really doing is saying, is it even or odd? Because numbers even, you get a 0. Numbers odd, you get a 1. Even, that's odd, 1. Even, 0. Even, 0, and so on. Okay, so by continually dividing by 2, starting at the least significant digit, we can turn our decimal number into a binary number. So you can guess what's happening now. There's 4 for you to have a go at. Don't forget what you got to do to represent the plus and minus sign in the front. Okay. Right, 123 represented as a binary number. Nathan, asked you first this time.
I got, was it 0 first for the positive bit, and then
Yeah.
I don't know if this is right, but 1 1 1 0,
Yeah.
and then 4 ones.
Well, you've got 1, 2, 3, 4,
Is
5,
that too
6,
many?
7, 8, 9 bits. Yep. So let's go through what you've done. So you must have started from 123. Yeah.
Yep.
And you when you do 123 over 2, you get 61, and you got a remainder. So your
Yeah.
least significant bit is 1. Yeah.
Should I not put that bit at the start to say it was a plus or minus then?
Yeah.
I'm getting a cool one. So
You got to do 7 bits and then put your 1 on the front. Because if you only got 8 bits, one of them is the sign bit. So
Right,
what
so
you've got here is
do you stop when you get to 8 bits then?
yeah, if you're using 8-bit words. So you've got your units, your 2s, your
Oh, I see.
4s, your 8s, your 16s, your 32s, your 64s, plus a
So
sign bit on the end.
So
Yeah.
I take a 1 off
1,
the
2,
end, do I
3,
then?
4, 5, 6, 7, 8. Yeah.
I see. I didn't see that 8-bit thing. I wondered where I stopped.
Yeah.
That's why I was just trying to get down to 0.
That's all right. Well, let's do this
I-
one, and then I'll give you some time to do the other 3.
I
Now
just
that
went
you
down
know
to
that.
0 on
Yeah.
on it.
Yeah, that's what I
So
thought you were doing.
61 over 2, 61 divided by 2. Also, that leaves us 30 plus a remainder. So we need a 1. 30 divided by 2 is even. So there's no remainder. We got 15 left. 15 divided by 2 leaves us a remainder. 7 divided by 2 leaves us a remainder. Yeah.
I was doing
3 and
mine
a
from the
half.
other way as well.
Yeah, you got to start
I
from
was
this
doing-
end.
Right, yeah.
You got to start from the least significant bit end. Yeah. You should end up with 4 ones in there. That's where I can see now you had yours the wrong way round because your 4 ones come in the wrong
Yeah.
place. And then the 0 on the front to represent your positive. So you've got 1, 2, 3, 4, 5, 6, 7 digits representing your number, and then the sign on the end. So now that you all know that, have a go at the other 3. So what I put on the right hand side there is the step by step of how the first one was done from LSB to MS. MSB is the sign bit. So you're working from right to left building your ones and zeros up.
Is it 1 1 0 0 0
1
0
1 0
1
0
1? 4 zeros.
0. Yeah,
Yeah. Yeah.
you're absolutely correct. Yeah.
hmm
Carter, can you join us and give us a second one? Jake?
Yep, I got it.
What you got then?
0 1 1 0 1 1 0 0.
You're absolutely correct. And I'll have Macca for the last one.
I didn't get that far.
Did you not?
No, it takes quite long to keep dividing them all.
All right. Have you done that one, Dom?
I've got it if not.
Yeah, go on then.
1
Jake?
1 1 1 0 1 0 0.
Yeah, absolutely correct. Okay. So that's relatively simple to switch either way, either to go from decimal to binary or vice versa. Okay. So having done that, we're going to have a look at another slightly different system now that can be used when we want to be able to display some digits of a binary number on like a 7-segment display. So it's called binary coded decimal, BCD for short, and it's now process for converting decimal numbers into their binary equivalents. Naturally live in decimal base 10 world, so most of the numbers we deal with are in base 10. And we need some way of, computers will store all numbers as binary numbers. If we want to display them to the general public in terms of an understandable system, we just displayed a load of ones and zeros. They wouldn't be able to work that out because they're used to base 10. So this binary coded decimal helps us to turn the displays, 7-segment display, to display numbers. Okay, so we've seen previously that an n-bit binary code is a group of n bits that assumes up to 2 to the n distinct combinations of ones and zeros. So we've seen how we can represent decimal numbers as binary, but the advantage of the BCD system is that each decimal digit is separately represented by a group of 4 binary digits or bits. So for the 10 decimal digits 0 to 9, we need a 4-bit binary code to cover the 10 different decimal numbers that we can possibly have. Okay? So the way that's done, if we look at the binary coded decimal, so we'll look at one 4-bit word, we've got the most significant bit representing 8, and the least significant bit representing the 1s, and then we've got the 2 and the 4 in between. So we start our possible combinations with 4 zeros representing the decimal digit 0. We go up to 101 represent a 9. Okay. The possible combinations beyond that are all not used as marked here. Hang on. Yeah. So all of these ones are unused combinations. If you're devising a digital system, you need to make sure that these 1, 2, 3, 4, 5, 6 options in the binary word cannot possibly exist. They can't happen. That they're not used options, and they should not appear, because if you do, you get a false binary representation and a display that looks like gobbledygook, if you like. What a good word that is. So if we look at this, the number 352 is represented by 0011 for 3. 0101 represents the 5, and 0010 represents the 2. Yeah. So each digit in the decimal number is represented by a 4-bit decimal binary code to represent the digits 0 to 9. So the use of this code, as I've already kind of said, is used in microelectronics and computer systems, useful in situations where binary coded decimal is intended to be displayed on one or more 7-segment LEDs or LCD displays. Many popular integrated circuits that can be configured to give us BCD output. So this is an example. We've got this 74LS47, which is a binary coded decimal to 7-segment display decoder. So although you could design the logic circuit that would turn these various A, B, C LEDs on to make up the number, you can buy a chip to do it in one go. So here's our 4 inputs, A, B, C, and D, of our binary number. It's not explicit, but I would imagine that A is the least significant bit and D is the most significant bit. So if we wanted to represent our a number 7 on there, we'd need 1 for the 4, 1 in there, a 1 on there, and a 0 on there. Should help us to display the number. That one would light up, that one would light up, and that one would light up to display 7. We'll see how that works. Well, they get the general idea. You don't need to understand at all that to be able to use this, you don't need to understand what goes on in here. It's a fairly complex logic circuit to achieve all of that, to operate these 1, 2, 3, and then the other segments of that display depending on the input. Okay?
Okay.
Yep. So what I'm going to show you now, that I'll put this diagram in my in the notes, but I got a little circuit demonstration, a little circuit simulation thing on the iPad that can just show how these 7-segment displays work. So I'm just going to share that with you now. So that's currently turned on, and if I operate these switches, you can see that the display is going to on this system is going to go hexadecimal. So if I turn on the most significant bit of the you see the display changing. Got no battery now. It's not very successful, is it? Damn meter keep coming up. So that goes from, as I change that least significant bit there.
Right there.
Let's go, champ.
You up?
Oh, sorry, I did. I thought I was muted. Talking to myself.
Six, 2, because that switch adds the 4s, the units, 2s, 4s. So if I operate that switch, it adds a 4 onto the display to make it take it from 6 to 2. Not overly successful. It's a little bit tricky, I find, to get the switches to work. That's kind of why I haven't suggested that you should think about getting it, to be honest. A bit tricky. I prefer the multi-sim, but it didn't have the 7-segment display. Probably a paid-for option on that. Okay, so you got the general idea anyway of the type of thing that you can do with binary coded decimal. Right. So what I'd like you to do is turn the 3 up the top, encode them to binary coded decimal. So each of them have got 3 digits. So you'll need 3 4-bit words for each of them, and then decode the bottom ones from their binary coded decimal into decimal numbers. All right. Right, Dom, what you got for the first one?
What's that? Encode the following decimals to BCD.
Yep.
I'll be honest, I didn't do it, but I'll do it right now if you want. 1 second.
I'll give you time to do them. What you got then, Dom? Go on, hurry up.
Whoa, you're pressuring me now. So you can't rush a masterpiece.
No, because that's 10 minutes ago since I started you on this. You've done the first one. Motivation.
All right. So. One zero. No, wait. I don't know. Next.
You've got to do a 4-bit word for each digit. So we want a 1. So the first one is going to be 0001.
Yeah. All right. And then
Yeah.
00111.
Correct.
Then 1000.
Correct. Yeah?
Yeah.
Jake, you got the second one?
0 1 1 1.
Yeah.
0 0 1 1.
Yeah.
1 0 0 1.
Correct. Macca, third one? He's hanging back. Nathan?
0 0 1 1. 0
Yeah.
1 1 0.
Yeah.
0 0 0 1.
Correct. Have you got the first one going the other way as well, Nathan?
2 and 8. And then
Yeah.
the last bit, I got 10, but I thought it was only up to 9.
Yeah, that'll be my fault.
Yeah.
Change that to 2 zeros. That'll be another 8. Yeah. I was in a bit of a hurry. Sorry about that. Right. Jake, you got the next one?
1 no wait 9 0 5.
905. Yeah. And the last one is 1 2 6 5. Sorry, 4 and 1 is 5. 1 2 5. 1 2 5. All right. Yeah, so that's binary coded decimal used in displays. Now, what would normally happen, because using BCD wastes some bits of storage, your computerized system would store the number as a binary number, convert it to a BCD number, and then display it as a code using a 7-segment display, because it uses less memory, and also arithmetic operations like plus, minus, divide, multiply on these binary numbers is much easier to do on the actual binary number than it is on the binary coded decimal number. Yeah, so we'll do one more little bit before we break off for a quick drink. Digital representation of analog signals. So, although for the electronics for processing, analog and digital signals are quite different, so they are very different. There's often a need to be able to represent analog signals in digital form. So, if we're going to have computerized control systems, we need to be able to represent an analog signal in digital form, either as part of an output to a system or an input from something else. So it brings in the need for us to be able to convert analog signals to digital and vice versa. Okay, so the conversion from analog to digital would be carried out with an analog to digital converter, ADC they're shortened to. So it takes an analog signal in, one that is a level between two limits that we talked about before. So it might be 0 to 15 volts or 4 to 20 milliamps. So e.g. 0 to 15 volts, say. Yeah. And the ADC converts that into a digital number of a given number of bits at the output. Okay, so that means that a computerized system can take an analog signal in, have it converted into a digital number, and store it in memory and use it in the program to run the machine. Conversion of digital to analog is carried out by a digital to analog converter, or DAC. It takes a digital signal in, so a series of ones and zeros representing a particular analog voltage level, and then will give us a voltage out, for example, between 0 and 15 volts, or between 4 and 20 milliamps, for instance, output to control something, maybe at the speed controller of a motor, or the opening and closing of a valve to allow flow, etc. Yeah. So that's the overview of what analog to digital and digital to analog conversion is. So the example, we can take a 0 to 10 volt signal from a pressure sensor. So it can be anywhere between those two limits of 0 and 10 volts. We can use an ADC, an analog to digital converter, to convert that into a binary number of a given number of bits. We'll look at that in a minute about how you might choose a particular number of bits to represent the pressure to a computerized controller. And then an example of digital to analog conversion is that we'd have a binary number stored in a control system somewhere that represents the speed you want the motor to run at. We use a DAC to convert that into, for an example, a 4 to 20 milliamp signal, where the level of that current signal represents how fast we want the motor to run. Yep.
Yep.
Now, analog signals can be represented. So the way they represent these signals is in the form of a binary word of a given length. So if we take an example of a 4-bit binary word we're fairly familiar with at this time, it can represent 2 to the 4, which is 16 different voltage levels. So if we take that 4-bit word as representing a 0 to 15 volt signal, it would do that in 1 volt steps, because we've got 16 voltage levels to represent, and we've got 16 16 voltage levels including zeros. So you've got to count the first one and the 15th one. So there's 16 levels, and we've got 16 possible combinations in the word. So 16 over 16, it represents it in 1 volt steps. So for example, 7 volts would be represented by the digital number 0111 in the binary word. Yeah, 7 volts equals 0111. Yeah, 10 volts would be 1010, and so on. Okay, so when we represent that voltage with just a 4-bit word, it's quite easy to see that it's a pretty crude representation of that straight line analog voltage represented by the blue line going through the middle. And that brings on to something called quantization error. Because the analog signal is represented in discrete steps, there's an inherent error between the digital representation and the actual level called the quantization error. The quantization error is the difference between the analog signal being put in and the closest available digital value. So if we take, for example, if the actual analog voltage in our 0 to 15 volt example was 6.5 volts, the closest representation to that 6.5 volts is 7 on the on the digital representation system because that would round up. Yep. So what we have there is an error of up to half a volt, because 6.6 volts would be rounded up to 7. 6.3 would be rounded up to 7. 6.49 would be rounded down to 6 in this system. Yeah. In general, the quantization error is given by plus or minus the step size of a 2. So our step size is 1. Yeah. Divide that by 2. Our error is plus or minus 0.5 or half a volt. Yeah. So that's our quantization error is plus or minus half a volt in this case. Okay. So we can improve that, as you are now going to discover, by increasing the number of bits. What I want you to do, and I'm giving you time to do it, right, is to calculate for an 8-bit word, a 12-bit word, and a 16-bit word, what the step size is and what the quantization error is from that. Okay, so 8-bit word is 2 to the 8 combinations, 12-bit word is 2 to the 12 combinations, and a 16-bit word is 2 to the 16 combinations. That's for a 0 to 15 volt signal. Okay, so what I'm going to do is give you a generous break until 5 past, and come back and we'll go through those when we come back. All right, speak to you then. 5 past. Right, let's see where we got to now. Dom, have you done the 12-bit word?
Oh dear. I seem to have lost my calculator. Oh, there it is.
12-bit word, Dom.
12-bit word. So if you do 16 over 2 to the power of 16, that'll give you.
We were doing the 12-bit word.
Oh wait, not 16. Yeah. Wait. Yeah.
So we also have a 2 to the 12. Yeah.
Oh, what did I say? Someone else.
You said 16.
Okay. So that'll be 3.90625 times
No,
10.
ain't 3 volts, is it? That's not going to be bigger than this one. That's 4,096 combinations.
In a bracket. That sorts everything out.
That's plus or minus as well. No, and quantization there is plus or minus. So what's 16 divided by 4096?
0.0039.
391. Same number. I keep to the same number. 3 significant figures. 391 volts. So your Q error is
Plus
that
minus.
plus or minus that over 2.
Is it? Okay, yeah.
Which I get as plus or minus 0.20195 to 3 significant figures.
Yep. Me too.
Yeah. Jake, do you want to try the other one?
Yeah, can do. Obviously 16 over the 2 to the 16.
Yeah.
There was 65,536 different combinations.
It's a lot, isn't it?
Yeah.
There are a few.
I got 0.000244.
Volts. Yeah.
And then that
That's the step size. Yeah.
is
Divide that by 2, you get
0.000122.
is the error. Yeah. So as you can see from that, if we keep adding 4 bits on, we gradually reduce that error. I believe the only one I've really got any knowledge of, but Mitsubishi PLCs, certainly the series I worked with, uses 12 bits for its A to D converter, because there's a trade-off between how many bits you use. So obviously you can see that the more bits you use, the smaller error you get in representing the analog signal. However, it's a trade-off there in the amount of memory it needs to hold those extra bits. So 16, you could go up to 32 and you'd increase even more. Also, there's the cost of the processing of the extra bits. And there comes a time when adding the extra is not worth anything because you don't need it any more accurate than that. So 12-bit, 16-bit at the highest level is the ones that I've come across. Not heard of any D to A converters that use more than 16 bits. There might be some out there. Okay?
Yeah.
Right. There was just something I thought of while we were having a break for me to just talk to you a little bit about why you might use in a modern system converting your analog signals to digital. If you have a large site where you've got some remote plant, it's going to be a bit rough, and you've got things like pressure sensors, flow sensors, temperature sensors in there, so on, that give you analog signals. Yeah, you might also have digital signals as well. If you have a control room that's a long way away, control room, with your main control system in it, if you try and send those analog signals, so 2-wire 0 to 15 volts or 2-wire 4 to 20 milliamps over a distance, let's say, of 300 meters, one, you've got problems. So direct analog connection. You've got problems with volt drop of the signal, so losing voltage over the resistance of the cable. And you've also got a major issue with interference from other signals. So that's if we had our analog sensors given 0 to 15 volt or 4 to 20 milliamps or any up between any other limits, we try and connect them directly using normal electrical wiring techniques over distance. And I choose the example 300 or 400 meters. We can have where these cables run together with other, particularly main systems, we can get interference and we'll have problems with volt drop over distance. Okay. If we switch to control room again, and you've got your PLC, for instance, in there, yeah, and then you've got your plant, okay, and we have local conversion of analog to digital. So what we have is ADC in here, analog to digital, that converts all our analog signals to digital signals and then sends them all down a network cable as digital signals to the PLC. Okay, if we think about an analog signal getting interference, so if we have a signal that goes like this, so I'll go to a different color. We've got an analog signal that does that, for instance, over time. Yeah, if that gets interfered with, that can end up looking very much not like what it should be. Okay, if we take a digital signal that is a series of ones and noughts, yeah, if that gets interfered with, it might look like this, have some wobbly bits on the top and on the bottom, but it still looks like a series of ones and noughts. Yeah, and so by transferring those analog signals to digital signals locally next to the sensors and plant, and then transmitting them over a specially designed network cable to the PLC, and that can be two-way as well. So you could have analog signals this end, converted to digital and going that way. You could have the digital signals transferred this way and converted to analog signals to control your motor at the other end. And there's an option for these network cable to be very high speed fiber optic as well, so you can go over really long distances. Okay, so that's just kind of giving you some reason as to why you might want to use analog to digital conversion, and where it can become an advantage in distributed systems where you're looking at a system over a wide area. And this network cable, we got the internet, the plant could be in Australia and your control room technically could be in the UK, and you'd still get that control between them. Okay?
Yep.
So hopefully that kind of gives you a little bit of a background as to why you might be learning about this and some of the advantages and disadvantages of each of the systems. I mean, your analog signal's got the advantage that it's infinitely variable between two limits, but the disadvantage is that can be interfered with easily. Your digital signal's got this step thing where there's an inherent quantization error, but it's less susceptible to interference. Right? Yep.
Yep.
Right. What I want to do, just to finish up this week, is to start looking at a topic where semiconductors are used in power electronics. So preempting a look next week at power supplies. Just a bit of a refresher. The diode, if we remember, the symbol is an arrow with a line across the front. Yeah, and its action is that it will allow current to flow in this direction, yeah, in the direction of the arrow, but it won't allow current to flow in the opposite direction. So it's like a one-way valve. Among other uses, among other things, the diode is widely used in power systems as rectification. Anyone know what that term means, rectification?
Rectifying something.
That's kind of not got the same meaning as rectify in terms of put something right. The process of rectification is AC to DC. Convert an AC signal, an AC waveform, to a DC waveform, usually a sine wave. Okay? So in terms of a power system, so we go on basic AC to DC power supply. First thing is, if we got an input of 230 volts, we'd want a transformer. So 230 volts. Iron core. Secondary. Let's have 16 volts. DC. Yep. AC, sorry. So we're putting AC in here, and we're getting AC out here. Yep. Now what we can have, first thing we're going to look at is what's called half wave rectification. If we put in this circuit here a single diode, and here's our load resistor. Okay. Now,
No.
if this is plus and minus AC, when and this is our AC waveform, so we're going to have a positive half cycle, plus in red, a current will flow this way, yeah, through here in red, and at the output we'll see the positive half cycle of the waveform. In the negative half cycle, in green, we're trying to send current in this direction, but the diode won't allow it. So we don't get no current. In the green half, and we lose that half of the AC cycle. We don't get no output. And then when that comes back to the red half cycle again, we get the red half cycle like so. Yeah. So making that larger, we get an output that is half a cycle, lose half a cycle, another half cycle, and so on. So it's a pretty crude, and your average output voltage will be somewhere in here, average DC level. So that's half wave rectification. If you want a very simple DC supply, you're also, if we looked in detail here, if this is the AC waveform, you're actually losing a little bit more because you've got this. We must remember that we've always got 0.7 volts across there to turn it on. So again, I have to change color again to red. What we're actually getting with the DC is we're losing a little bit there as well which is the 0.7 volts. And we're jumping off there at 0.7 and coming on a bit late. So you're losing slightly more. So with that half-wave rectification, out of the 16 volts, you'd actually get 15.3 here at the peak. Okay, but the average meter reading voltage will be much lower than that, about 7.5. Okay, so that's half-wave rectification. Have any of you come across that before?
Not
Dom?
really.
No, Jake?
Nope.
Not at work or anything?
No, not really.
I mean, I probably just looked over it, just thought, right, cool.
Yeah. Half-wave rectification is not going to be very common anyway, because it's so easy and relatively cheap to buy a bridge like I'm now going to show you that'll do the full wave rectification anyway. So you might not come across half wave in any sense. All right.
Yeah.
So how do we do full wave? Right. Let's just. Again, we'd have our transformer. $230, 16. Yep. This time what we have, and four diodes in what's called a bridge. Like so. Anyone seen that symbol before? Okay. Now what you have is you always have two diodes point towards the positive DC terminal. So this is this diode and this one, and this one are both pointing towards the positive terminal. And the other two diodes point away from the negative DC terminal. The AC goes on the outside too. So we take our DC off there and there. And that's our load. Okay. So again, if we take a red half cycle, positive half cycle, the AC waveform, in that half cycle, current goes down this wire here, down this diode, through the load, through this diode, right, back up here and back to there. So the output in the red half cycle is like so. Yep. Note that the current through the load is going in this direction in that half cycle. Yeah. If we then have a blue half cycle, where this terminal is positive and this one's negative. The AC current is going that way, flows up that diode, and goes the same direction through the load as did the red half cycle. But then it takes this route back up to here. So it's starting here and going back to there. But notice that the two current arrows, both the red and the blue one, are going in the same direction through the load. So we have an output that goes blue, red, blue half cycles as the output waveform of full wave rectification. Yep. And for fairly obvious reasons, the DC level that you would get from that is much higher, up there somewhere. Yep. So if you measured the output with a meter, you'd measure that average DC level. All right. So that's the difference between full wave and half wave rectification as using diodes. So what you can do with this bridge is you can either build a bridge out of separate diodes, or you buy a package that's got 4 diodes already built in it, just 4 terminals coming out of the package, 2 marked AC and 1 marked plus and minus DC. And that's just a 4 diode bridge rectifier. Okay, a number of different ones taken from tiny currents up to several tens of amps. All right, so there's a widespread use of diodes in power supplies. So I'm going to leave it there this week. We finished a little bit early. I'm going to try and, what I'll do is I'll put set notes together next week that starts that off properly, so there'll be some better, tidier drawings for the full and half wave rectification. See if I can put together some models on the multi-sim system to show that working. And then we're going to look at some other ideas in power supplies, like how do we smooth out this waveform so it's not lumpy, we get rid of the ripple, and then how we can use other electronics to control that output still further. Okay?
All right.
All right. So we'll leave it there with half and full wave rectification. And I'll see you guys next Tuesday, 8:30 for maths.
Right.
All right?
Oh, aren't we on half term?
Yeah, we did.
No, you're not.
Oh.
Because
You what?
you're not. We're working.
Ah.
Unlucky.
Anyway, did you guys see my email to Omar?
No.
I asked him to bring materials forward to 5:10.
I'm not
I don't
today,
think-
man.